Welcome back. The last talk for today is going to be benign, tempered, or catastrophic taxonomy of overfitting. We're going to have Neil Mallinar speaking, who is a PhD student at UC San Diego. And I believe Pritam will be joining to speak in the second half of the talk. Just take it away.
Yeah. Hello. Thank you very much for joining me today at 4 p.m. I appreciate your time. I'm going to be talking to you today about some work called Benign, Tempered, or Catastrophic, the Taxonomy of Overfitting. This paper is in review currently. This work has been ongoing for the last year in largely Misha's lab with some help from a student here at UC Berkeley, a co-first author of mine. And we are very inspired by a lot of the theory and empirical works that many of the people in this room have presented, and we've come up with some interesting experiments and theoretical ideas that we want to share with you. If you came in December to the Simon's workshop, Pritam presented an early version of some of those experiments, which sort of motivated some of the other theoretical angles that we get into, and I'm looking forward to talking to you about it. I should put an asterisk here that we do call it a taxonomy of overfitting, but we'll consider some underfit methods as well. It's primarily a taxonomy of overfitting because interpolating methods sort of led us to these results, and they're perhaps more interesting. But to really round out the fact that we have a taxonomy, we will consider some underfit methods, and we'll show how they fall under the taxonomy as well. So without further ado, these are the people who contributed to this work. So Jamie unfortunately couldn't be here, but I think he'll be around for the rest of the week, is a student at UC Berkeley, a PhD student in the DeWeese lab. Amir-Sam is a student in Misha's lab who's here. Partha is a postdoc. You all know Misha, and Pritam, who's now at Apple, has contributed heavily to this work. So we'll start with the classic story of overfitting. This is something that you should all be very familiar with. If you type overfitting into Google, you will find these images, and it should be no surprise. A lot of the conventional wisdom for overfitting says these sort of jagged and wiggly lines are not good. So these images are often characterized by some reasonably clean decision boundary that you want to do regression on or classification, and these sort of wiggly lines that contort themselves to fit noise in your training data. And we're told that this is very undesirable, at least classically. So on the left, I've given an extreme example of what this really undesirable type behavior is with these types of contorted polynomials. But on the other hand, modern thinking says to just interpolate, and you can generalize fairly well. And maybe these kinds of wiggly and jagged lines aren't so bad. And you might end up with a function like what you see here on the right, where you have some train set with noise. There's a true function that you want to learn, and your predictor actually models it fairly well while sort of having these spikes to fit the label noise. And it leads us to the question of how harmful is overfitting for standard deep neural networks. And this is sort of what motivated us to begin this study. Before continuing, I'm going to give a little bit of notation, which I'll use to define certain things in the next few slides. And then when we get into the kernel regression setting, we'll give more notation as needed. We have some estimator trained on n samples from an underlying distribution, x cross r, and we denote it by f hat sub n. There's the population risk for mean squared error, something you're all familiar with. We'll use r star to denote the optimal risk, where we take them in over all measurable functions here, the Bayes risk, and then r sub n is the expected risk of an estimator trained on n samples. And the question, which Nadi set up very well, and a lot of the people that you've been hearing, is what is the limit as you add more samples? This is a question of consistency. So what is the limit as n goes to infinity of r sub n? So I'll return to these two examples that I presented earlier of the sort of classical thinking about overfitting and this modern thinking of overfitting. And I'm going to call the classical setting catastrophic. So this limit goes off to infinity. And this is a very, very undesirable behavior. And we'll call this benign, where the limit approaches R star, the optimal. And you'll notice there's some gap in the middle. And we have all probably observed a number of functions that lie in this middle regime. And we're going to put a name to it. And we're going to call it tempered overfitting. So the limit converges to something that is neither catastrophic nor benign. So there is some harm incurred by overfitting, but perhaps it's not so bad. I'll note in the case of a classifier, which we will study first experimentally, these infinities would be replaced by the risk of a random classifier where you'll use the 0-1 loss. And so instead of infinity here, you'll have a k minus 1 over k for a k-class problem. So I'll return to the question of how harmful is overfitting for standard deep neural networks. And I'll start with a simple experiment, something you've all seen now a few times in yesterday and today's presentations. We train a wide ResNet. It's a version of a residual convolutional network on a binary version of CFAR10. So we take 4 of the animal classes, 4 of the object classes. And on the left here, we don't add any label noise, and we plot the classification error on a clean test set over the number of training samples. And we see that as you add more training samples, your test error improves. And on the right, we flip 30% of the labels. And you've seen this experiment before. Spencer presented it. Nadi had a similar slide where as you add more training samples, you basically have this 30% classification error when you flipped 30% of the training labels. So this is not altogether surprising. And one thing to note here is that perhaps in the pursuit of a benign method, you would want, even in this case, when you're just doing binary classification, as you add more data, you would want some improvement if you're very resilient to the noise. And that will sort of motivate some of the later ideas that we're going to get into. I'm going to extend this experiment in the following way. I'm going to put the label noise on the x-axis. So on the classification, label noise is the probability of flipping a label to a different class. And I'm going to keep the classification error on the y-axis, where we're measuring against the clean test set, where we haven't perturbed the labels on the test set. And a few things to note on this plot. A catastrophic method is a random classifier. So with any amount of label noise, you're just outputting random labels. This is very bad. We'll say a benign method lies along this bottom line here until you flip 50% of the labels. So as you add more label noise, if you're really not harmed, you'll essentially get an optimal classifier until you flip half of the labels, in which case the best you can do is random. And now I'm going to plot lines for different values of n. So where before I changed n on the x-axis, I'll put n different lines for different values of n. And what we see for these ResNets that are interpolating is that the error is actually changing as a function of the label noise. This is something we've observed before. And as you add more samples, while at very low label noise, there's some improvement, you're sort of nearly always lying along this kind of line, especially if you look here at 30% error up to 50%, more data is not really improving the test performance for these neural networks that are interpolating the training set. Yeah.
This is the actual test set, not test set, right? On the y-axis?
Yeah, this is the clean test set, non-perturbed labels. So the 0-1 loss on the test set with the normal labels, no flips.
Oh, okay, so
This is the excess.
So it is
This is the excess. Yes,
excess.
yes, it is excess.
Dimension of the really interpolate is 40k samples. You need a huge interpolator.
These models are they're interpolating in the training classification. So all of these models have 100% training.
How large is the dimension? How large is the dimension?
This is CFAR, so we're working with 32 by 32 images and 3 channels. So 3 by 32 by 32.
Training model, what you did is just like taking the label and some probability you flipped it.
Yeah. Okay. To the other class. In this case, it's binary. So you have one and you just flip it to the other class.
Why is it benign is 0?
Yeah, well, so even with 0 label noise, you can see that we have some non-trivial error here, but it's likely that we just don't have access to enough points. And what we're arguing is that in the case of a simple binary classification experiment, if you're not harmed by label noise for binary classification, even with up to 50% label noise, a consistent method should learn something that lies closer to this line right here. 0 is essentially like experimentally, I don't know that we'll get that with this finite sample.
So is the interpretation of this plot just that is no benign? Is the interpretation of the plot that is no benign overfitting in practice?
Well, yeah, in this experimental setup, we'll say that overfitting is not exactly benign when we call benign truly harmless interpolation, but tempered is not so bad. And tempered maybe more practically mirrors what we see in certain setups like this, where you can keep adding training data and you want to train your models and see how they improve. And we often see that training data sets are extended over time and we measure and test accuracy on them.
If there a method that is not interpolating and it's increasing, we find that some classical methods that essentially the excess risk converge to 0.
Yeah, well, I'm glad you asked because we'll actually show exactly those experiments very shortly, and you will see what a more benign method would look like in the case where it's non-interpolating, and that maybe alludes to some sort of tension between interpolation and true not being harmed by label noise.
So for the blue line, that says n restricted.
Yes.
So do you show, maybe I'll talk about this, but do you show theoretically that the middle lines will not approach the blue lines and goes to infinity?
Yeah.
There's only 4
Yeah,
cases.
we'll theoretically show that's the case, and we'll also theoretically recover the benign overfitting conditions that you are familiar with when you don't have a ridge, and that will be interpolating, but experimentally, kind of as Gil was mentioning, we will show that when you don't interpolate, you can actually get very close to this benign line here. But theoretically, we will show that this is the case. So an outline for where we're going to go, I'm going to give some examples in the taxonomy and generally how you might use this and put methods into different categories. I'll talk a little bit about some empirical results that we've shown using deep neural networks, which have motivated a lot of this work. And then finally, Preetham's going to look at overfitting in the case of kernel regression specifically. So some prior works, I know that I have omitted a lot, but we've sort of been inspired by a lot of works, and I can't include every citation, but we've really want to point out that when you take D being the input dimension and N being the number of samples, many of these works will find that benign overfitting is shown when D is larger than N, or when N and D scale jointly. And otherwise, you will get some work showing generalization error bounds in D and N. And our work is cohesive with all of this. And I also want to point out G. Lee and Telgarsky show some early stopped consistency of neural networks, and we'll look at some experiments in this realm as well. So really the motivation for a taxonomy comes from the fact that we're considering a problem where we're fixing the input dimension D, and we're taking the number of samples off to infinity. And in this setting, what we're calling benign is consistency. And something we had noticed is prior works will say things like when you have a lower fixed dimension, certain kernel interpolators are inconsistent. Rockland and Jai show that for the Laplacian kernel. Recently, Beaglehole, Belkin, and Pandit show that for some classes of shift invariant kernels, including the Gaussian kernel. And they'll say that in low dimension or fixed dimension, kernel interpolators are inconsistent. And what we want to say as well is that there are two ways to be inconsistent when interpolating. That is tempered, where you have a bounded risk as you add more samples. And what we'll show in the kernel regression setting is that this is a function of the label noise. And there's catastrophic, where you have an unbounded risk. And we want to motivate that perhaps being inconsistent in a tempered way is not so bad. And that's in line with some of the observations of deep neural networks saying fitting the noise is not so bad. We find that they are tempered, but we'll show that there is something, there are methods that are catastrophic.
Yeah, architecture does not change while you increase the number of samples.
In these experiments, we're fixing the architecture to be sufficiently large to interpolate as we increase the number of samples, but we do allow for changing architecture. And I think it would be interesting to look at what are maybe some principled ways that you might change the architecture as a function of n in order to maintain. But for the experiments we show in neural networks, we fix the architecture. So we'll point out some example methods in this taxonomy. On the left here, we have benign or consistent. And I'll just comment that in the ridged kernel, which we'll show later, and KNN, you're not interpolating. So I'll just call this benign fitting. You will have a consistent method, and it does approach the Bayes risk as you add more samples. And then you have the Nutter-Watson estimator with a singular kernel, which is an interpolating method that in our setting is benign. In tempered, where your risk is bounded between optimal and infinitely bad, we'll show experiments that interpolating DNNs under this experimental setup that we've presented are tempered. We'll also see that the Laplacian kernel regression without a ridge is tempered. And of course, the KNN with a constant K is tempered. This is something that we know. And then catastrophic, you have models at the double descent peak, polynomial regression with a degree equal to the number of samples. And what we'll actually show is that the Gaussian kernel regression without a ridge is catastrophic. So delineating between tempered and catastrophic allows us to create two settings in which we have these results saying Laplacian and Gaussian kernel are inconsistent. What we actually see, which matches some experimental results of papers by Misha, if you've seen, the Laplacian kernel is tempered, which is perhaps not so bad, while the Gaussian kernel in the ridgeless setting is catastrophic.
Do you have any examples of interpolating methods that are catastrophic?
Catastrophic interpolating methods. Yeah, I could just memorize my training data and then predict randomly on anything else.
The polynomial method, isn't it?
Polynomial regression, you said such example?
Yeah, also polynomial regression, right?
Do you have examples of any methods that don't fall into, it's indeterminate which category they fall into?
Yeah, so there is a consideration that the limit doesn't exist. As far as I know, there's no kind of non-pathological examples. Like if you're using a learning method we all use, I think this limit should exist. Maybe you can construct some settings in which you're constantly oscillating between, I don't know, getting better and getting worse as you add more samples. I'm not actually sure. It would be interesting. I don't know if anybody has any ideas about that, but it would certainly be interesting to think about if the limit doesn't exist, what does that mean? So I'm going to further give a sort of visual intuition for how example methods might fall into the taxonomy through an experiment where we're classifying a binary version of MNIST. So we're looking at even and odd digits, and I'm going to plot the same plot that I showed you earlier for a variety of methods. And we'll see at a glance how just looking at how the method sort of reacts to label noise sort of tells us whether you're falling into this benign category or not. So here we'll see KNN with some scaling of k as about log n. And what I'm plotting here is 1,000 samples, 10,000 samples, and 60,000 samples. And each of these lines is averaged over 5 independent runs. And you can see even up to some modest amount of label noise that the test error is doing fairly well. And it's bending towards that right corner, which is what we would desire of benignness. In the spirit of the early stopping results being consistent, we also look at a 1 epoch MLP trained on the same problem. And we actually see that even up to 40% label noise, we're having less than 10% test error on the clean test set. We'll look at a bit more of a complicated example of early stopping because MNIST is remarkably easy. So maybe this won't convince you, but we'll show you another example. And then on the other hand, 1NN, as you would classically expect, as you add more samples, approaches y equals x. And overfit MLP starts to look a little bit like a 1NN type model, where as you add more label noise, your test error is getting harmed, but not infinitely bad. So we'll say the methods on the left are benign, in this case, benign fitting, and the methods on the right are tempered. So I'm going to show a few empirical results on deep neural networks, and then we're going to look at overfitting in kernel regression. So I'll extend the earlier example where we took the binary variant of CFAR10, and I'm just looking at the full multi-class classification. This is a more complicated example. I'm training the same wide res nets. All of these models are interpolating the training data. Even at 90% label noise, I'm fully interpolating the training data. And something that characterizes being tempered, according to our taxonomy, is this roughly linear shape here that you get, whereas you add more training label noise, you get some harm in your test error. Another example we have, we'll actually simplify this just to drive the point home a little bit. We're looking at binary classification, and we're taking synthetic data sampled on the 10 sphere. And we're just putting all the labels to 1. And with some probability, we flip them to -1 and we train an MLP. So we're just trying to learn the constant function. And a consistent method would do pretty well. And you can see even as we increase the amount of training data from 300 to 360,000 simple MLPs, this is a 3-layer MLP, 1024 width. Simple MLPs are not learning the constant function in the presence of label noise, even at reasonably small label noise. So we look a little bit deeper at early stopping in deep neural networks. So this work that I mentioned before shows that some shallow and wide ReLU nets are consistent with early stopping. I think they use the logistic loss. We experimentally look at a problem where we train ResNets on a binary version of the Street View house number problem data set. So this is something a little bit more difficult than MNIST, a little bit easier than CFAR. And we choose the early stopping epoch for each of these points here based on cross-validation on the training subset. And we see on the left, when you optimally early stop, you're not interpolating, but even up to 30% label noise, you're getting a very negligible harm on your test error. And yeah.
So I can just see you choose based on cross-validation, which is noisy.
Yes.
So you are interpolating or not interpolating? Because
on the left, we're not interpolating. On the early stop.
But if you do it based on cross-validation on the, since you can't type zero, based on cross-validation the training set. What? Oh, okay. Oh,
yeah, sorry. We noise on one of the folds and non-noisy on the other fold.
Oh, I see.
Yeah, right. So we don't look at the held out test set in that process. Okay. Yeah, that's right. Yeah. So on the left, we see an example of a non-interpolating method that really does clearly bend towards that benign line, which is very desirable of a method that is resilient to label noise. And on the right, these methods are all overfit. They're perfectly interpolating the same data set. This is just a continuation of this experiment, and we see that you start to get this tempered profile. So to look a little bit more clearly at that, we look at the time dynamics in a regression problem for an MLP. So we take a ReLU MLP and we train it with full batch gradient descent. We sample data from a 5-dimensional sphere, and we take the labels to be 1 with some Gaussian noise. And we plot here the time in training, so optimization steps, and we plot the MSE for the train and the test set. And what you see is that in line with Nadi's slides earlier, up to a point, your train and test are following each other. So you're still underfitting the noise, and they'll reach this Bayes optimal value at some point. And then once the train MSE reaches down to 0, you see that the test MSE, as you start to overfit the noise, gets worse, but then asymptotes. And this is indicative of the type of tempered overfitting that we're looking at. And you can see we'll change the number of training points to n equals 200. It delays when you fully interpolate, but you still get the same asymptote with these ReLU MLPs. And we show for n equals 500, the same thing. We haven't shown a plot here, but one thing that I'll motivate is that if you change the activation function, you can actually get these harmful interpolation curves that Nadi had shown, where these will just go off. So that concludes the empirical section on deep neural networks. I'm going to hand it over to Preetham to talk about overfitting in the kernel regression setting.
Can you hear me? Okay, good. Thanks a lot, Neil. So I'm going to be, let's see, okay, good. So I'm going to be stepping in for Jamie Simon, who unfortunately couldn't be here due to a flight mishap. But it's too bad, but he'll be here the rest of the workshop, I think. And so he's really responsible for the entire theory part of this section. These are his slides that I'll just be presenting, but credit to him for these results. Okay, so to recap a bit, we've defined this taxonomy of the 3 different types of fitting behaviors that learning methods can exhibit in the asymptotic limit. And then Neil has presented a bunch of empirical results suggesting that standard types of deep neural networks, when they interpolate, don't actually overfit benignly, right? So benign overfitting means that even in the asymptotic limit, there's no asymptotic effect of label noise, right? A method that overfits benignly will be able to learn the optimal predictor even in the presence of label noise, but that does not appear to be the case in practice for many standard neural nets, right? Okay, so this begs the question that we have a lot of, on the one hand, we have a lot of theoretical results for when learning methods are overfit benignly. On the other hand, we have some practical experiments that suggest actual deep neural networks don't seem to be benignly overfitting. So how do we resolve this disconnect? There's 2 important aspects here. The first aspect is our setting is slightly different. So we're considering a fixed task and just scaling the number of samples. In particular, a fixed dimension, and just scaling the number of samples. This is in contrast to many prior works where the problem scales up in accordance with the number of samples. Right here, we're not scaling the problem and the samples. We're just considering a fixed problem and saying, how does this learning procedure on this fixed problem behave as you scale samples? So that's the first potential factor explaining the disconnect. The other important factor is going to end up being the types of assumptions that you make on the data, and particularly the spectrum of the data. And so we can understand that factor better in the kernel setting, which we're now going to study. So in general, the broad question we want to understand is, can we understand when learning methods behave benignly, tempered, or catastrophically? This is a very complex question, but we can simplify this question for kernels, and we can actually get a fairly complete understanding of this picture under some heuristic assumptions. So that's what I'm going to talk about now. Also, please feel free to interrupt me at any time with any questions. I will do my best to answer them. Okay, so as a sort of summary of the results, for kernel regression, we can understand which type of overfitting kernels exhibit in terms of the spectrum of the kernel on the data. Okay, so essentially any kernel that has a ridge is going to be statistically consistent. This is standard. The interesting part is what happens for ridgeless kernels that interpolate. And by playing with the type of kernel, you can get either tempered or catastrophic behavior. So for example, a Laplacian kernel, so here the x-axis is the number of trained samples, the y-axis is the test MSE. And for the Laplace kernel on the hypersphere, even as you send samples to infinity, you get some sort of bounded test risk. On the other hand, for the Gaussian kernel in any fixed dimension without any ridge parameter, that as you send samples to infinity, at some point the test MSE shoots up, and demonstrating catastrophic overfitting. So we can actually we can prove things about this under some heuristic assumptions, but this is what the experimental results look like. Yeah.
Just to make sure.
Yeah.
In which case it does interpolating or not?
No. Yeah. So this is not interpolating. This is just demonstrating essentially like any universal kernel. If you set the ridge parameter appropriately, you will get consistency. That's just that. This is a standard result. Yeah.
What is the
Yeah, good question. This is, I think, the setting where we're just learning the constant function plus Gaussian noise. So the constant can be, yeah. Any other questions? Yeah.
Might be kind of minor advantage, but I think like Shiyu and Sasha's result on ridgeless Laplacian kernel, like their lower bound was only either for like even or odd dimensions. But does this show up at all in the empirically, or does it just true in general? That was like a technical part.
Oh yeah, good question. Yeah. So there is an inconsistency result for the Laplacian kernel in fixed dimension. I think the lower bound itself is fairly weak in terms of dimension. I believe it was exponential in dimension. This is like much worse than that lower bound suggests. And I don't think Jamie's techniques depend on the parity, but there's also some heuristics in the techniques. So I think Jamie will know the correct answer. Experimentally, it didn't seem to matter. I think, so. Yeah. Oh yeah, this is a good point. That this taxonomy applies to learning methods generically, whether or not they fit the training set.
But what is benign?
Right. So benign really it means the same thing as statistically consistent. Right? We're just using literature because it's been used in the literature. So this taxonomy makes sense whether or not you're fitting the training data. It's perhaps particularly interesting to study for interpolating methods in the context of understanding better how interpolators behave.
Yeah, maybe it's out of the scope of your work, but do you find like some solution how to fix that to somehow it will not interpolate and benign?
Yeah, it's sort of I think there are many possible fixes. Like if you simply don't interpolate, like you do one epoch training, then that seems to be consistent. Yeah, I think regularizing appropriately, like in practice, people do label smoothing for when they have noisy data, and that's one method of regularization that will help some of these things. I think that's sort of easy fixes that could work here.
I just wondered if you explored any other kernels that was closer to being benign when you don't regular.
Yeah. So I think we didn't find any closed form kernel that is benign. So there's like a spectral condition. If you have I'll maybe get to the theory result. There's a particular spectral condition that a kernel needs to satisfy in order to be benign, and it's very fragile. It's a very fragile condition. It's a similar condition as in Peter's work. Like you need a particular kind of spectral decay to be benign. You can get it artificially. You can like take the Gaussian kernel and add a delta kernel to it. Then that's effectively like adding a ridge to your kernel. Right? So you can cheat and get a kernel that has an effective ridge without you explicitly putting a ridge there. But it is kind of cheating. That you want like a natural kernel. And yeah, we don't have a natural closed form kernel that is benign.
Do you look at the NTK?
Did we look at the NTK? Yeah, so we have some results on that later. If you take the NTK, yeah, I'll do it later. If you take the NTK of standard networks, they behave like tempered, which is sort of what you'd expect, because if you do the actual neural network experiment, you also get a tempered behavior.
I was wondering, like, how do you read off, for example, that the left part is benign? Shouldn't that be an axis, which is the fraction of noisy training labels?
Oh yeah, good point. So really, this is benign if this asymptotes to 0 for all sort of fractions of label noise. In this case, because we're in the regression setting, it's like if things behave linearly with respect to the noise, because it's just additive Gaussian noise. So you can just test it for a fixed level of noise, and you should expect things to scale normally. So another way, like, yeah, there's really, in the regression setting, it's really about variance. You can consider the experiment where you just try to learn the constant 0 function plus additive Gaussian noise. And then this is looking at the variance of the predictor in that setting. And so now you can just scale the noise, and it's possible to scale because everything is linear.
Will you cover the intuition for like why the like the tail of the kernel of the spectrum of different answers is like?
I will cover the results. Whether I have good enough intuition myself is another question. I think Jeremy has some intuition, and that was also consistent with the benign overfitting results for Peter and others. So maybe we can sort of come up with something. Okay, there's some intuition. There's actually, yeah, I should say, I think there is good intuition for this. Jeremy has like a way of thinking about eigenmode learnability that I can try to discuss a little bit. Yeah.
Any other questions?
Okay, so I'll try to give a brief overview of the results and how the proof works. I'm not actually an expert in this myself, so I'll do my best. But we're in this kernel setting where the inputs X are sampled from some measure, which we will assume to be uniform over the hypersphere. The goal is to learn some function that's the ground truth plus noise. We're going to learn it with kernel regression, where we have some PSD kernel, and if D is the n samples from the data set, this is the form of the kernel predictor, the regularized kernel predictor for some regularization delta thing. Some review. It's helpful to think of kernel learning in terms of the spectrum of the kernel. So just to review the notation that we'll use, if you have this kernel that you can think of as an operator on functions, and once you have this operator, you can decompose this operator into its spectrum. So for example, for shift invariant kernels, this is just looking like shift invariant kernels diagonalized in the Fourier basis, right? And the frequencies are the eigenfunctions. So, but in general, we can look at a kernel in terms of its eigenfunctions and eigenvalues. And for natural kernels, we expect the eigenvalues will decay. Function index, yeah.
Already said this. I just wanted to clarify some terminology that I think relates to other questions. So just so I understand. So consistency means that as n goes to infinity, you get the test error. You get the optimal test error. Yeah. Benign, you're defining benign as being as n goes to infinity, you recover the optimal test error on the clean distribution.
Yeah, I'm not redefining consistency. I want benign to mean exactly the same thing as statistical consistency.
Okay, but so then so then consistency means you get the noise rate. It should be getting the noise rate, not the zero rate.
So the optimal function for the clean distribution is the same as the optimal functions for the noisy distribution.
But if the learner doesn't necessarily return that predictor on the noisy data.
So a consistent learner, when trained on noisy data, should return the optimal function for that noisy data, for the noisy data distribution, which I claim is the same as the optimal function for the clean data distribution, right?
In the limit, yeah, but there are these weird situations. Okay, I guess this relates to the point about the limit, the non-convergence. Okay, so I guess it's the non-convergence. It's just that, I mean, all I'm saying is that I did the lines necessary to establish that I'm getting the benign effect from our early stopped paper. And I didn't use the limit characterization. I need to do a couple lines on top of the finite time guarantee. So it wasn't direct. That's all I'm saying. So I was trying to see if I missed something. Is it quicker than a few lines, or?
I'm not sure I understand exactly the question, because yeah, we are only considering the asymptotic limit, though. We're not considering finite
I
sample
think that's
behavior.
okay. That's
Yeah, as in your paper, you also had sort of finite sample guarantees, right? About
and there I had to work a little to get the right thing, but okay.
oh yeah, so that might be possible that if you want to do sort of give some kind of finite sample, there might be a difference.
But yeah, I understand what you're saying, that for in the asymptotic limit, once you're on the right side of a half, then it's the right thing.
Yeah.
So, but yeah, it was the okay. Now I understand. I'm sorry, it was my fault. It was just a question about the finite sample part. Okay.
Yeah, and we can follow up also. Any other questions? Questions about the setting. Right, so this is sort of kernel setup. And it's helpful to decompose everything in the kernel eigenbasis, including the ground truth function that you're trying to learn. So you have some ground truth function that you're trying to learn f star of x, and you can decompose this into the basis of the kernel. So this is just, for example, doing the Fourier transform of your ground truth function in the shift invariant case. Okay, now how do we think about kernel regression? You can equivalently think about kernel regression as linear regression in some lifted feature space. And it's convenient to think of the lifted feature space in terms of the eigenfunctions, using the eigenfunctions as features. So you can write the kernel as the sum of this inner product of the eigenfunction features. So this is just going to be to give some flavor of the tools that are used for the analytical results. Okay, so. And because equivalently it's a PST kernel, and so you can use this feature map, this eigenfunction feature map that will induce this kernel. Inner products, according to K, is exactly the standard inner product in this lifted space, where this lifted space is evaluations of. So if how do you lift X into this lifted space phi of X? You just evaluate all of the kernel eigenfunctions at X. So, for example, evaluating each frequency, each sinusoid at X, and things are weighted by the eigenvalues. And so you can study, you can study kernel regression as linear regression, standard linear regression in this lifted feature space, and that's the object we want to study. We want to study the test MSE of this object. Okay. Now the analytical tool. This is a heuristic approximation. So this is the part of our results that is not rigorously mathematically proven, but this is a analytical heuristic that has been used in the past in papers in physics, and we've also tested this heuristic experimentally. So this is a sort of a universality assumption. So what we're saying is we have these lifted features, right? And we want to study linear regression with the design matrix as the lifted features. Let's study like a proxy for this design matrix, which is let's let the lifted features, instead of the two features, let's let them be multivariate Gaussians with the right covariance structure. So this is approximating the two design matrix as with just another matrix that matches its second order moments. Right? And we're now going to study this Gaussian object as if it was a real object, and this will work under the assumption that the two test errors are going to be the same. And there's empirical evidence for this universality type claim, and it also has some proofs in special cases, although not in the case of our work. Okay, but so is the rough kind of strategy clear? Like this is the main type of assumption. Yeah.
Are you assuming this only on the test data or training data as well?
No, I think everything. So just assume you're now studying a completely different linear regression setting, where you have Gaussian design matrix, but Gaussian design linear regression, but with covariance given by the kernel eigenspectrum.
In that case, we have sufficient necessary.
Yes, but we want to now study like not the joint scaling limit. we want to study just a finite, like fixed dimension into infinity scaling. That's right. Yeah.
We did that, but without Gaussian, with some Gaussian.
Yeah. 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 So like your benign overfitting paper gives spectral conditions for benign overfitting in this case. We now just want to understand
His upper and lower bounds under some Gaussian.
Right. But also with requiring like dimension, like scaling both the covariance structure with N, right? It's in the ratio. So okay, so then it should like this should be consistent. Let me see sort of what the results are. Let's see if they're consistent, because I know they're consistent with your results for the benign case.
I see there were upper and lower bounds there that held in the infinite dimensional settings, you know, as a function of the spectrum. Okay.
Yeah.
You know, under a weaker condition, just sub-Gaussian.
Right. Okay.
And not
right. So yeah, so if they're equivalent, then these things should also show that they're tempered if there's like power law spectral decay.
I mean, the bounds are like constant factor.
Okay. Yeah. So let me like we have some bounds that should predict sort of the actual exact constant as well that seem to agree with experience, which is kind of interesting. So let's see if it's consistent with this. So maybe let me skip this part because yeah, there are many papers that derive sort of the effective what the tester should be in this Gaussian or like under this Gaussian assumption, including Peter's paper and many others. Let me skip this part. The point is just that if you make this Gaussian assumption, you can write down fairly simply like what the test MSE should be. Okay, and so here's the theorem that comes out of it, the assumptions, and let's see how that is consistent with this. So this, okay, so the point of this theorem is we want to say how does the spectrum affect the kind of overfitting, and so this part is the benign overfitting condition that's in Peter's paper, which is if the spectrum decays just slower than a power law, just barely slower than a power law, then you'll overfit benignly. On the other hand, if you have any kind of polynomial tail, then you will exhibit tempered overfitting, and the limiting test MSE will be given by exactly by the exponent. So the rate of the spectral decay is exactly the constant that determines how far is exactly the gap to benignness. I don't know if this is this.
We didn't have we had bounds up to a constant. So
okay.
I mean, we did a calculation in the appendix for that case that showed that this thing was bigger than sigma squared.
Yeah, I think this is sort of an interesting prediction. It's also we have some experience, so it sort of aligns up with that.
We had a constant factor gap between upper and lower bounds, so certainly get an alpha.
Yeah, sounds good. Yeah, I think the sort of Gaussian case has been studied in many papers, including this. Yeah, the point is just sort of, it's nice that this alpha sort of exactly determines this gap, and as you send this alpha, close to 1, you get this benign case, and as you increase the alpha, you get further and further from benign, and once you're faster than any power law, like if you decay something I to the minus log I. Once you're faster than any power law, then you're catastrophic. And that's sort of aligns with this alpha. This alpha is 1, it gets to benign, and as you increase the rate of the spectral decay, when alpha increases, and when alpha gets, when you're faster than any power law, then you're catastrophic.
Sorry, what's beta?
What is delta here? Delta is the ridge. So this is just ignore delta. Like if you have any ridge, you're going to be benign. This is interesting mainly in the business case. Did that?
Yeah.
Okay. Yeah.
Is this a statement for there exists an I, or for all I this seems to be the case for this?
Yeah. So we put this under the for all I, but I expect these things of kind of robust, like as long as it's roughly power law kind of decay.
What about the last one? Like
Oh yeah. This is just beginning of this is just saying if lambda I is I to the minus I log I. I to the minus log I. Yeah, so they're all for all I statements. So this is the experiments that we saw previously. There's a question about whether we tested NTKs. So the spectral decay of ReLU NTKs is similar to the decay that you get from the Laplacian kernel. And in both of these cases, we see the tempered overfitting. Right. Well, here's looking at its alpha dependency, and so particularly if you vary the spectral decay of the kernel and you look at the test MSE empirically, it appears to track with what this theory, what Jimmy's theory predicted, which is that you get this exact. Yeah. What is this is on the hypersphere. Oh yeah. Yeah, I guess it should track. Yeah, I'm not sure. Some experimental issues and getting conversion that close to one or something. I'm not sure though.
Does it need to be the same also for all that? Or just
yeah, well, does it need to be the theorem, like the proof we did was sort of very fragile to that, right? But I don't think the actual result will be fragile. Because yeah. Like in practice, when we did the DNN experiments, it appears that almost anything that interpolates is tempered. And so I think this tempered overfitting is like fairly robust behavior. It shouldn't require any kind of fragile spectral conditions. Yeah, so the point of the sort of analytical results is to give us insight into what's going on in deep networks, and at least in the kernel setting, we can understand it, as well as like many of these prior papers have understood exactly how the kind of overfitting depends on the spectral decay. We would like to extend this understanding to deep neural networks. So an open question here is, so one open question is how do we get a more complete understanding of when deep neural networks overfit benignly, or overfit in a tempered fashion, or overfit catastrophically? And empirically, it seemed like all natural things we tried interpolating DNNs tempered, and we don't know how to sort of make natural design choices that are both interpolating and benign. I think this suggests that benign overfitting might not be the best kind of conceptual framework to think about what's happening in interpolating DNNs, and maybe tempered overfitting is an appropriate substitute. But there's many open questions here. We really only have a complete understanding for this specific kernel setting, and even then the proofs were not fully rigorous. So it's open to see if we can make them completely rigorous. Yeah, then.
So the plots that Neil was showing earlier, they had the error on the clean distribution being basically the same as the level of noise. Is that right? And would that correspond to like alpha equals 1 in your theory? Or?
Oh no, that alpha is completely different from these alpha. Yeah, that alpha is changing the spectral decay of the kernel, which would correspond to something like changing the architecture or the activation function in the right way.
The amount of tempering, I guess, is that going to affect?
Oh yeah. That's I see. Yes. That would definitely correspond to alpha equals 1 here. Although this is also classification, and that was regression. So yeah.
Can you go back to slide?
Oh, sorry. Yeah, alpha equals 2. Yes. Yeah. It is very interesting to me that in the classification setting, it seems that the amount of label noise you inject in the train set is very close to the amount of noise that you get for the train. It's not effective noise. Okay. This is what one nearest neighbors would do. It would reproduce the noise in the train set exactly. Interesting that interpolating that's behaved like this too. Oh, yeah.
Speaking of which, early on, the first step, the proofs for USD are very similar to the
Yeah.
So can you like falsify the neural nets just to use the neighbor? Or do you have examples where the behavior is different, or is it just the neural nets being kind of like nearest neighbor?
It depends on what scale you look at, I guess. The nearest neighbor in like neural networks definitely behave better than nearest neighbor in such settings, right? It's just that maybe the asymptotic noise, the noise profiles.
I'm not saying that neural nets don't perform, or not that don't perform better than the better accuracy than the nearest neighbor, but more that the effect of overfitting is similar to the nearest neighbor.
Yeah. I don't know how to falsify that yet. I think you can even do experiments for which we've done in past papers of take your entire domain and only add noise to some subset of the domain, like only add noise to cats or something. If you're training on CFA, don't add noise to all the classes, only add noise to cats. Now, if you were doing one nearest neighbor, then you would expect that at test time you get noisy predictions for cats, but maybe not for other classes. And that's that you get that for interpolating neural nets as well. You get the same local noise affecting things locally for neural nets as well. And so there's sort of suggestive evidence that oh yes, the other question has a paper that in the limit of wide and infinitely deep networks, the NTK converges, or like the effective NTK converges to it.
You actually get so if they're reasonable.
Yeah, I haven't been able to make the connection mechanistic, like but at some scale, they seem to behave similarly. Sorry, if there are no further questions, thanks for all of the questions, and yeah, happy to follow up offline as well. Yep. Yeah.